Hello, my name is Steve Akers. Welcome back to the Boston University Metropolitan College lecture series on the topic of blockchain. This is lecture 2, where we're going to dive into a few of the details of payment verification, key management in hardware deterministic wallets, and in transaction validation. So, as we learned last time, this is a network of cooperating components. We have wallet software that works on your phone or your laptop. It carries your private key and your public key for cryptography reasons. It issues transactions from a wallet into the full node layer of the network, and those full nodes validate transactions which move them on to the mining layer, with the ultimate goal being to bundle those transactions into a block, give them an immutable name called a hash, and then build it into a blockchain, all over and over and over again, so that transactions can get processed continuously. So last time we looked at the taxonomy of a block, and that it has a hash which describes its own contents. It has the hash of the block that preceded it in the chain. That's how they get linked into a blockchain. And then it had a special kind of hash structure for the transactions themselves called a Merkle tree. The Merkle tree is shaped as a balanced binary tree, as a computer scientist would call it, so that one can have each corresponding set of hashes hashed together to end up with a Merkle root. So you end up with, in the case of Bitcoin, a 32-byte number that describes all the transactions in the tree. And that number can tell you if anything changed, because as we learned in lecture 1, a property of cryptographic hashes is that if any of the information that went into a given hash changes, the number changes quite a bit. No two different messages will have the same hash, so it's a perfect naming mechanism. It's also built like a tree so that we can walk that tree very efficiently and find a given transaction to make sure it's in a given block, to tell that transaction's been mined in the blockchain and confirmed as a payment in the blockchain. As we learned last time, the blockchain gives us a mined block every 10 minutes, and once 6 of those consecutive blocks have been mined from our transaction, our payment is confirmed. So much work has been done that an attacker could not have undone all that work and changed one of our transactions. What this relies on is this Merkle tree structure, and there's a property of a Merkle tree that says if you take the log to the base 2 of the number of transactions, that will yield how many transaction hashes you have to verify to tell a given transactions in the tree. So basically, in our idealized example where we have 4 transactions, we only have to verify 2 of those hashes to verify that our transaction D, for example, in the case shown in the slide, is contained in the tree. But where it gets interesting is, if you remember our block header from block 629243, that had 2,082 transactions in it. Given this property of logarithms, all we have to do is compute 11 hashes, not 2,082, to verify that we have a given transaction in that tree. And we know what block it's in, so we can tell how many blocks have been mined. So by using the Merkle path to our transaction, we can use just 11 hashes and verify any of the 2,082 transactions are somewhere in that tree. The reason this is important is, going back to our discussion in lecture 1, as we know, our wallet has to keep track of the transactions that it is responsible for out on the public ledger. The coins are never in our wallet. The keys to unlock transactions are in the wallet, but the value, the unspent transaction output Bitcoins are sitting out there on the ledger, marked down and in our account. So to constantly monitor the chain, the wallets will build up their own idea of which public key hashes or addresses belong to a specific wallet, their public keys. So the wallet will constantly probe the network. So it sends out special commands to the full nodes saying, I would like the Merkle path for these transactions, please. And there's a special structure they can build these addresses into called a Bloom filter, which when issued to the full node returns a series of these paths to right where your transaction is. So your wallet can very efficiently, with the help of the full nodes, build this set of transactions. So in a wallet, in a real piece of wallet software, it'll show whether you're your transaction is confirmed 100%, 60%, 40%, and that depends on how many blocks have been mined since your transaction went into the blockchain network. There are also special nodes that sit out on the blockchain network like full nodes, but instead of downloading an entire copy of the blockchain and maintaining it like a full node does, it's a simple payment verification node. It just keeps copies of all the headers of the blocks. And those exist on the network, and they make these same requests for Merkle paths and payment verifications to the full nodes for blockchain explorers and code that sits on the web for people to go explore whether a certain transaction was ever paid or not. So all that log business that I was spouting was strictly to support all this payment verification. Because as we saw in lecture 1, it's very important to know your payment is verified before you let someone leave your Porsche dealership with a Porsche or something. This, of course, all relies on public-private key pairs. And last time we learned that the public key is just a big long number we can let out of our wallet, and the private key is a big long number that we keep in the wallet, and we never let the private key out. They're generated on one of these magic elliptic curves, so they represent points on the curve, and they can verify that they belong to one another, the public and the private key, by using this digital signature algorithm function. When we generate an address, this is a little more detailed view of what I showed you last time in lecture 1. We take the public key, just a big long number, and Bitcoin loves hashing things multiple times. So it hashes that public key value into a 32-byte number, the SHA-256. We talked about that last time. Then it takes that hash, which is 32 bytes long, it creates a 20-byte or 160-bit hash out of that, which makes it a little smaller, a little more secure. Then it runs this encoding step, which turns it into our address, which is the series of numbers and letters at the bottom. And that can be turned into a QR code sent to someone, they can pay us. So since you're all alert students, you're saying, okay, Steve, that's great. We have these public-private key pairs. If I send all these addresses out based on my public key, I must have to have a whole bunch of these private keys to go along with them. So how do I store those and manage those and all that? And you'd be right. So in these hardware deterministic wallets, Ledger makes one. That's a British company that makes a small device. It could fit on your keychain. You can plug it in your computer, and it'll manage all this key material for you. Trezor is another company that makes one of these. So they're hardware devices you can plug into a computer and have it work with the wallet software. Also, in your phone, there's sort of a built-in crypto chip that works with a wallet you can download to your wallet. So it has an ability in that hardware to generate what's called a master key from a master seed. And there's some Bitcoin Improvement Protocol, BIP, standards. BIP 32 and 44 govern the way you build these keys. So they generate the master seed, that generates a master private key. And that private key in this special hardware, which has special mathematical functions, hash function, can create a generation of children private keys. So I have my master private key and a sequence of children. Those children can have children and so on. So I can generate a large number of these private keys, and they're all maintained in the wallet. Then, as we saw, we can take any of those private keys and the wallet can generate a public key on that elliptic curve. So it's a convenient way to have lots of keys working as pairs. Now, there's another special set of hardware in these devices, which allows us to build public keys and private keys that we call extended. So the hashing function adds a little information to it, and it makes an extended private key, extended private master key, or an extended private public key at a certain level on that tree I showed you. Now, the interesting property of these are that you can generate public keys that can have public children. So you can split your key space into the private half and the public half. I know you're saying, why in the world would I want to do this? Okay, the reason this is important is, say you're a Boston University, Met College, Master of Science in Project Management graduate, and your boss says, congratulations, you just graduated. I want you to take command of a new project to put cryptocurrency on the website for our online store. So, brimming with excitement, you get your front-end team, you get your back-end team, and your security people, and you say, great, you know, on our front end, we're going to enable payments to our online store and various cryptocurrencies, and your front-end team will talk to the back-end team, and they'll break your architecture into two parts. Back in the back of your data center where it's all safe and secure and sound through multiple firewalls, you'll have your database and your online store function, and that's where you could put your wallet with private key material. It connects securely to the front end over SSL, extremely secure cryptographic methods. And in the front end where you could be attacked from the internet, you would never put anything private out there. So the question is, how do you get public keys out there so you can generate these addresses so you can get paid into your wallet for your company? So as people access your website from the front end infrastructure, they have to come in over the web. Your security team would be apoplectic if you ever put any private material out there. So you have to find a way to put the public keys out there. But because you've seen this course on blockchain, you know what you need is an extended master public key. Your front-end team will be overjoyed because they have an API which can accept this from your wallet, and it's just a public key. And it sits out there, works with their library, and it generates new public keys as you need them. So as people hit your website, you can generate them an address based on a public key that belongs to your master public key, that belongs to your master private key back in the deep heart of your safe data center. So the public key cannot sign transactions and claim any payments. That's the job of the back-end infrastructure. But you don't need that on the front-end infrastructure. So you generate all the addresses you need off this master public key and send them out. People pay that with their wallet software, and then you claim the payments later from the back end. And you're a superstar with your boss. Now what I want to talk to you about is the exact details of how we validate a transaction. In lecture 1, I showed how Anatoly had sent me a Bitcoin and how I spent it, part of it for coffee, and sent change back to myself and all that. And I made the statement there were locking and unlocking scripts, but I didn't describe what they are. The reason we have these is in the network, we have this protective layer that looks like the half moon. It's like a shield protecting the miners from bad transactions. So when the wallets generate a transaction, what the full node validators have to do is make sure that the person claiming a payment actually has the public and private key that goes with the payment they received that allows them to spend it. So when Anatoly locked that payment down to me, he locked it down to my address, which was tied to a specific public key. I have to produce the private key and the public key to claim it and send it on to Starbucks to pay the barista. So that's this layer we're talking about, this protective shield in front of the miners, because we don't want the miners to waste their time and energy, because that's very expensive, mining bad transactions into bad blocks. So let's go back to our example. I want to get Tanya Zlativa to go down to Starbucks, and we'll talk a little strategy, buy her a cup of coffee. So we go down there, the barista says that'll be $5, and I say, great, let me pay you in Bitcoin, if you remember that. So I have, in the past, have published this address, and in transaction ABC, Anatoly has locked down that Bitcoin to my address, which I gave him in my initial request for payment. So in the block somewhere is that payment. It's an unspent transaction output, and I'm going to use that as the genesis of or input to my transaction DEF to Alice. And I'm going to prove I can unlock that. So on the blockchain network at time T0, I've received the Bitcoin from transaction ABC, and that's tied to a certain public-private key. My wallet finds that, it pulls it into the wallet and pulls certain information out of it, which we'll see on the next slide, and it builds a transaction DEF with a little bit of Bitcoin for $5 to Alice the barista and a bunch of change back to me. It generates my address to pay myself change. It uses Alice's address that she sent me in her request for payment. At the end of all this, Alice is paid. But it's reliant on me finding the Bitcoin in the first place I got in transaction ABC, and then splitting it into two and sending it to Alice and myself with the right public-private keys. This is what a transaction looks like on this slide. So in ABC, Anatoly had built a transaction document, which specifies my address, and he built a locking script that locks that to my address. I'm building this new transaction, DEF, and I'm going to take that transaction and the locking script from Anatoly's ABC transaction. I'm going to copy it into my document. I'm going to build a new locking script, and I'm going to explain to you what all these locking scripts are. I'm going to build a new locking script with Alice's public key hash as one of the main parameters. It's up to her to prove she can spend that later by producing that public key that she sent me. But for right now, all I'm concerned with is taking the locking script that Anatoly sent me and proving I have that public key and I have the private key that goes with it. So I bundle all this up and I compute 2 hashes on it because Bitcoin loves to double hash everything. On that hash, I take my private key that goes with the public key from transaction ABC, and I sign that document. And that computes a couple of values, and that's called this digital signature. Like I showed you when I explained digital signatures, Alice sending a digital signature to Bob in lecture 1. What I'm doing is I'm sending that signature and my public key from transaction ABC along to the network with the locking script that I have to satisfy to spend the Bitcoin. So right now I've signed a hash of this whole new document, and I'm sending that on to the network. Transaction scripts are written in this old 1960s type programming language that probably existed in the space program. And it's a very limited set of instructions. So what they let me do is take a public key hash and duplicate it, or take a public key hash and push it on a stack, which is, you can think of it as a computer puts these things in memory on top of one another, like you'd go to the cafeteria and put plates on a stack in the cafeteria. So it's limited in scope, so it's called Turing incomplete. I can't write a general purpose program that branches and loops and does things repeatedly. And the Bitcoin designers did that on purpose so that I could validate these transactions with these small limited instructions, but an attacker couldn't put a bad instruction in to bring the network down and loop forever. So that's why they picked this, and I think this is an indication of their brilliance, because they've used just enough technology to do this, not too much, not too little, and they didn't go invent something new and whizzy. They used something that existed that did the job, so it's pretty cool. Okay, so now what I want to do is walk right through the stack operations that verify this transaction. The various opcodes and operands shown at the bottom are numbered 1 through 7, and I want to show the corresponding stack operations shown at the top on the actual stack verifying the transaction. So at time slot 1, the instructions are to push the signature for transaction DEF up onto the stack. So we do that. Time slot 2 says take this public key Steve has supplied with that signature, push that on top of the stack. So now at time slot 2, I have the signature and the public key on the stack. Then the next instruction says duplicate, op-dupe, the value on top of the stack. So now I have 2 copies of my public key, which I've supplied with a transaction, on top of the signature that verifies the transaction. Then it says op hash 160, which says turn that top public key value into a hash 160 public key hash. And it does so, and now I have a public key hash instead of 2 copies of the public key and a signature. Then it says push the public key from the original transaction up onto the stack. So now I have 2 copies of a public key hash, and then the public key, and then the signature. So then the next instruction says verify that this public key hash from the transaction and the one you computed from Steve's public key go together. Make sure they're equal. They are, so they are popped off the stack. So what I've proven up to this point in time is that I have the public key in my possession that generated the address that created the public hash that Anatoly used to send to me. Now the last step is I have the public key and the signature. So I've verified that I have the public key. I want to prove I have the private key that goes with that public key. I pop the public key and the signature off the stack. I run a public key elliptic curve digital signature algorithm verification function on it called decrypt, and that returns true if it corresponds to my private key. It does. It returns equal. So the last step, step 7, is we push true onto the stack, and then the full node knows it can move this transaction on as validated to the mining portion of the process. That's what unlocking and locking scripts mean to us. So when we bundle up a transaction, we have to have these locking and unlocking scripts so we can prove we are who we say we are, basically. So now that we've seen how a pay-to public key hash with one signature verifies a transaction, there are a couple other types worth mentioning. There's a multi-signature transaction, which involves multiple public keys. So the example would be if one had a business partner and a lawyer they wanted to include in a transaction, so 2 of those 3 had to sign the transaction, they would supply 3 public keys for that. In case the business partner became unavailable, the lawyer could sign for the remaining business partner. So that's a multi-signature transaction, and it just basically indicates how many of the 3 signatures are required. You can have 2 of 3 required, 3 of 3 required, whatever. A pay-to script hash is a type where one just takes the multi-signature footprint and hashes it down into a redeem script and supplies the required number of signatures. So if we needed 2 out of the 3 multi-sig signatures, we'd have 2 signatures and the redeem script, which is a hash of the 3 public keys. So those are additional transaction types that we ought to mention, because when I get into the lecture 3 and we talk about executing swaps in the Lightning Network and some of the scaling initiatives, multi-signature wallets come into play, and it'd be good for you to be familiar with the concept and remember it from this lecture. Okay, so in our next segment, lecture 3, just to set that up a little bit, Bitcoin and Ethereum platforms will be compared. Now, fundamentally, Bitcoin is a cryptocurrency platform. It's there for payments, so it moves value from one key pair to another. It's just a straight public ledger. With Ethereum, they built a public ledger, but they want to take on the ambitious goal of becoming the world's computer, or running code that's compiled into the blockchain on command from transactions. So it's a very different concept. Ethereum contains all the aspects of public blockchain, but it takes on the added burden of running an Ethereum Virtual Machine, and it has its own programming language, and these are compiled into programs called smart contracts that go on the blockchain, and these are Turing complete programs. With Bitcoin, as I explained in the transaction validation code, we limit the functionality of that to a Turing incomplete language. So a nefarious attacker cannot bring down the network with a denial of service. With Ethereum, you could write any kind of program you want. You can jump and loop and use memory to your heart's content. So you could introduce an infinite loop and deny service to everyone on the blockchain. This Turing completeness is a challenge to protect against that. What the designers of the Ethereum protocol did was they introduced the concept of fuel or gas. When one initiates a transaction to execute on the network, one buys gas funded by Ether and executes a transaction. If they execute a smart contract that runs code, that gas is the limit or the amount of time that the network is allowing a program to run. So with these smart contracts and things of that nature, you give it gas, there's an upper limit on the amount of gas you can buy, and then if you go into an infinite loop, you'll run out of gas, and the network will protect itself from a denial of service. So in summary, in this discussion, we've explored why blocks are constructed with Merkle trees, how payments are verified, how public-private keys not just help secure transactions, but are managed in wallets so you can build secure e-commerce infrastructure. And then we walked right through a transaction validation, instruction by instruction, so we could understand this Turing incomplete language that validates transactions in Bitcoin. Then we look forward a little bit to the Bitcoin and Ethereum networks and how they might differ. We'll go into all the details of Ethereum, smart contracts, and how that public ledger runs in lecture 3. So Thank you for your time and attention. I look forward to seeing you in Lecture 3.